program. So today's for this session we have a speaker from Thailand, Dr. Dinesh Balasubramanian. I would like to introduce him by presenting his recent achievements in his research. Dr. Dinesh Balasubramanian is currently pursuing his postdoctoral fellowship in the area of battery thermal management, System of Electric Vehicle for Mechanical Engineering Division, Faculty of Engineering, and Center for Alternative Energy Research and Development, Konkan University, Thailand. And he is also working as assistant professor in Department of Mechanical Engineering, MEPCO Seleng Engineering College, Sivakasi, Tamil Nadu. Since July 2017, he has acquired B in Mechanical Engineering under Anna University, Coimbatore, ME in Automobile Engineering from Madras Institute of Technology, Anna University, Chennai, and PhD in Mechanical Engineering from Madras Institute of Technology, Anna University, Chennai. His major area of research are alternative fuels, diesel engine combustion, emission formation, battery thermal management system, phase change material, etc. He has published 40 research papers in SCI journals, and on his credit, he is having a H index of 20, I10 index of 28, and with a total citation of 1416. So I present to you all Dr. Dinesh Balasubramanian. Over to you, sir.
Thank you very much, sir. So it gives me immense pressure to deliver a lecture in this FDP conducted by PDA College in Karnataka, and I would like to express my heartfelt thanks to the management principal and the organizers of Department of Ceramic and Cement Technology for giving me such an opportunity and to explore my perspective on the impact of phase change material in battery thermal management system in current EV system. So the today's session is scheduled with respect to this particular agenda. So initially we'll just go through a brief introduction about EV, history of EV, and what is the major impact of battery thermal management system. Then we will just move further and try to understand what are the recent research progress that is actually carried out with related to battery thermal management system.
Hello, Dinesh. There is
Yes,
some
sir.
disturbance at the background from your side. Yeah, it is okay now.
It is fine, sir.
Yeah,
The audio is clear.
Yes.
Okay, fine. So the today's agenda is focused in this particular perspective that initially we will just go through a brief introduction about EV, history of EV, and try to understand the importance of a battery and the need for battery thermal management system. Then we will just progress further into the recent research progress that is actually carried out in battery thermal. Yes, sir.
Sir, again there is some disturbance at the background.
Whether my voice is not clear?
Your voice is clear, sir, but there is some disturbance at the background.
I hope my side it is clear, sir. Whether I need to check any other participants have to mute.
No, everyone is muted. It's okay.
Hope whether it is clear now, sir.
Yeah, it is clear. It was in the background. Your voice is clear anyway. We can continue.
Okay. Okay, fine.
Yes, sir. Go ahead. Continue.
Okay, fine. So in most often cases, I would like to start the presentation with respect to the recent research, the recent news that is here, and try to call the research topic that we are going to carry over in today's session. So Flipkart and Zomato. So Flipkart partnered with Mahindra for its EV initiative. Moreover, Zomato also commit 100% of adoption to EV, especially for their transportation purpose by 2030. It means that these news are there in air for nearly 2 to 3 days back. And Tata has installed over 400 EV charging stations across India and targeting 700 more stations by the end of December. So it seems that there are here and there the news about EV in most often cases in the recent newspaper. So according to this, India is poised to be one of the largest electric mobility market in the world because of the population in particular in coming decade, with the government push to curb pollution and reduce reliance on import, especially dependent on fossil fuels, because India is one particular nation who's uh, spending huge amount of money for importing fossil fuel, and that is the need why India is focusing much more on transition from its fossil fuel based transportation sector to EV. And Indian government is also pushing forward based on various policies to allow the electric vehicle market penetration in the automotive field. So the road of EV adaptation, a review of government targets and policies. Talking about this, state policies have outlined a good mix of for promoting EV adoption in their own regions. And I hope both Karnataka, Telangana, and to be in particular, the south of India is somewhat completely covered based on these particular policy. And all these policy have been approved, and the progress is moving on in the positive direction. So the road tax exemption complement the same to purchase subsidies and should be implemented at the earliest. And these okay, fine. And these EV policies target to supply a huge amount of incentives for electric two-wheelers, e-rickshaws, good carriers, which is about a limit of 30K, whereas electric cars would receive an incentive varying from 10K to 150K. And the government also planned to make public charging station accessible for every 3 kilometers in Delhi. And whereas talking about the policies that has been approved in Tamil Nadu and Karnataka, is having a different charging station policy scheme according to their own state government. And this is the current news that is alive in air for past few weeks about EV. And talking about the population of EV, the penetration of EV in particularly India by 2014 was very minimal. But as you can see that as year keep on get progressing, the penetration of EV is allowed to be at a greater extent. And as described earlier, both Flipkart, Zomato, and other leading e-market transportation sectors have tried to come up with all their delivery vehicles to be converted into EV by 2030. So based on their particular prediction, the Indian nation would have nearly a huge number of EV vehicles, especially two-wheeler based vehicles by 2030. And talking about the impact of this EV related to the existing internal combustion engine, based on the unit sold by 2010, the percentage of vehicles sold based on pure internal combustion engine was enormously high by 2010. But as the year keep on increasing, you can just see there is a huge drop in the sales of pure internal combustion engine based vehicle as the year keep on increasing. And currently we are here by 2020 and past, and based on this particular prediction, merely by 2030 or 2040 there won't be huge trace of pure internal combustion engine based vehicle in this current scenario. And these internal combustion engine based vehicle will be alive by the name of either hybrid vehicle or plug-in hybrid vehicle. So based on this particular prediction, the internal combustion engine will completely get degrade, but it will be alive by the name by an alternate name known as either hybrid vehicle or plug-in hybrid vehicle. So based on this particular prediction, as the trend shows that the future is with fuel cell or EV or plug-in hybrid based vehicle to make an emission-free mobility. So thus, this is the correct time to accelerate the research work in this particular field to get sustained in this current scenario. And talking about the history of electric vehicles, so nothing is new under this horizon. So electric cars has been around for more than 100 years, which is closely which is closely started at the time of the internal combustion engine itself. So it was in 1832 the first crude electric vehicle was developed, and it was in 1893 the first commercialization of gas powered car engines was introduced. If you just see this very closely, both was initiated as the same time scale, but due to some unavoidable reason, the electric vehicle was suppressed to a greater level, and for past nearly 100 years, the internal combustion engine was ruling the automotive sector to a greater extent. But even at that particular time horizon, electric cars gained popularity, particularly among the society humans. So because think about the starting issue and the pollution that actually occurs from internal combustion engine in late 19th century. So we need to have a particular additional setup for cranking your engine, and whatever the emission that spit out from the internal combustion engine would be enormously high. So at that particular time scale of 1899, the society women highly prefer to travel by means of an electric vehicle rather traveling or adapting to the internal combustion engine. And next to that, Edison takes on the electric vehicle by making use of battery in 1901, and in the same time scale where the first electric vehicle was clipped with the internal combustion engine to come up with a new terminology known as hybrid electric car. So it was in 1901 the first hybrid electric car was introduced to the market, but it take merely 100 years. So the first mass production of Toyota Prius were occur in merely the starting of 20th century. So, but whatever the invention that occurs about hybrid was there in 19th century, in the starting of 19th century. So it took merely 100 years the incorporation of an electric module along with the internal combustion engine and make it into a commercialized part. And the decline of electric vehicle actually happened in the time scale between 1920 to 1935, where people have straight away started to switching from electric vehicle to internal combustion engine based vehicle. One particular reason is because of the easy refueling and the easy maintenance, whereas the weight carrying capability. So all these eye-catching properties try to move the automotive manufacturers and the research and development units to work more on internal combustion engine based vehicle, and thereby there was a huge decline in electric vehicles and at this particular time scale. And the inverse happened actually in the time scale of 1968 to 1973, where the gas price start to soar to a greater extent, and people were thinking to seek an alternate to the existing internal combustion engine. And there were once again the electric vehicle was there in the newspaper by the time scale of 1970, where over the moon with electric vehicle. So NASA tried to propel its rover vehicle by means of an electric vehicle module. So after that, the talk about electric vehicle was alive in particular in the leading automotive manufacturing parts. So the next generation electric vehicle was introduced as a prototype in 1973, where the General Motors developed a prototype from an urban electric car, which was the company displayed in the first symposium on low pollution power system development in 1973. So it was in the time scale of 1973, the first electric vehicle electric powered four-wheeler was introduced to a prototype or a symposium based gathering to all the automotive manufacturers in 1973. So from there, once again, the electric vehicle gains its own attraction among the automotive manufacturers. And it was in 1976 the first mass production of hybrid vehicle was initiated. I hope we have already seen it. The first hybrid vehicle invention was there in year by 1901, and it took merely 100 years to reach its mass production. It means that for these past 100 years, only the internal combustion engine was ruling, pure internal combustion engine was ruling the automotive market field to a greater extent. And after that, the hero of the current electric vehicle comes into picture. It was in 2006, the Silicon Valley based startup takes on electric cars. So the Tesla Motors Silicon Valley based startup announced it will just produce a luxury sports car with a range of 200 plus miles, and thereby creates awareness to all the automotive manufacturers all around the world to accelerate their own research and development efforts team to focus much more on the alternate energy source. There is nothing but the electric vehicle. So this is where the electric vehicle was initially started along with the internal combustion engine, and later it was suppressed to greater extent by the internal combustion engine, and once again it has emerged itself as a leader and have gained its own market in this current automotive field. And let me just give a brief intro about electric vehicle. So any vehicle propelled by an electric drivetrain draining power source from a rechargeable battery or a portable, refillable, or electrical energy source like fuel cell, solar panel, whatever it is, which is manufactured for the use of public, would be kind as an electric vehicle. And the main key points that you need to focus on the advantage of electric vehicle is it doesn't emit any harmful emission as like the internal combustion engine. So that is where it gained more popularity, especially in a highly populated country like India and the highly polluted state like Delhi. So that is the reason why the Delhi EV policy focus much more on penetration of especially electric vehicle to a greater extent in their own state. So EV has no tailpipe emission and reduced air pollution in cities due to CO2, SOx, and NOx and particulate emission. So all these emission can be suppressed by a greater level. But if you just try to compare the well to well level, if you whatever the energy that the electric vehicle required is electricity, and this electricity can be produced by means of any thermal power plant. So it means that your particular vehicle won't emit emission, but for electric vehicle, the thermal power plant would emit emission. So that is where is the difference occurs between the electric vehicle and internal combustion engine based vehicle. So that should be taken into account when talking about the pollution in a broad manner. But our particular topic is related with the recent research progress on the battery thermal management issue. Until now, we have tried to have some glimpse, some ideas about EV and the recent technology development in EV. And now I'll just try to push forward the idea about the battery thermal management in the current scenario. So till now, I have discussed that there is a huge penetration of electric vehicle in the automotive market. But if you just try to see this particular news, so the battery fire put even BMW and Ford. I hope you are very much aware about these two leading automotive manufacturers. So battery fire issue has put even BMW and Ford to back foot. Sorry for it. So back foot just as the electric vehicle takeoff. So because of this particular battery fire issue, even leading automotive manufacturers like BMW and Ford are taking a back foot in their electric vehicle penetration in the automotive field. And this news was there in 16th October 2020, which is nearly 1 year back. And they have also tried to make fun of this particular issue to a greater extent. So vehicle going up flame aren't new in this particular electrical era. So they have coined this particular electrical vehicle transition as an electrical era and estimated around 1,71,500 cases of battery fire, especially for recent 3 years. And this is about the Hyundai electric vehicle Kona. And Hyundai considered global recall of all its electric vehicle Kona after battery fire report. So it is that all leading manufacturers are facing one particular issue in common, that is a battery fire, such as BMW and Ford as take a back foot in their electric vehicle penetration. And moreover, Hyundai electric vehicle Kona has called upon all its recent electric vehicles that are sale. So it has called upon nearly 77,000 of Kona EV that has been sold worldwide, and they have recalled all its vehicle to work on one particular issue, that is because of this battery fire. And this is the particular image of electric vehicle Kona that has been faced with the battery fire issue.
Hello, sir, you have muted yourself.
Okay, sorry for the interruption. Whether can you hear me?
Yeah, yeah.
Okay, fine. So I hope I have been discussing about the issues of battery fire faced by the leading automotive manufacturers. Even BMW, Ford, and Hyundai are facing this particular issue, and you can just see the impact of battery fire issue on the vehicle. So this was the image that was captured in Canada. I think so. I have not quoted that particular link to have a brief idea. So this is the impact of battery fire issue. And our topic discussion would be focused on the basic idea about battery and the impact of battery fire issue on the vehicle. So this is what is our presentation is going to be focused in the upcoming slides. And talking about the battery population, so in most often cases, we are just propelling towards the lithium-ion battery in this current scenario, and we'll try to understand what is the need, why the research is much more focused on lithium-ion battery in the upcoming slide. But it was in late 2015, the impact of annual lithium-ion demand was very minimal. But as the years keep on increasing, you can just see the demand for lithium-ion battery is going to be keep on increasing, and the dominant amount, the dominant percentage of lithium-ion demand would be especially there for the passengers EV. Either it can be either two-wheeler or four-wheeler, because by 2030 they have pledged themselves as uh, the Indian nation would transport all its e-market transportation vehicles into electric vehicle. So the demand for EV would rise to a drastic level by 2030. And talking about lithium reserves worldwide, so the Chile, Australia, and Argentina is having a huge lithium reserve by its maximum extent. And after that, there are very minimal traces of lithium in the remaining countries. So it is also agreeing well with the below pictorial representation also. So the Chile, Australia, and Argentina are having the major lithium reserves, and even India is also having an lithium reserve of around 1400 ton, which is very minimal as of compared to its demand by the end of 2030. And based on another statistical data, it has been reported that for the financial year 17, the India import of lithium batteries is of only for 384 million, which has been raised to 1.2 billion by the financial year 2019. And now we'll try to understand the basics of lithium-ion battery, and we will just move forward to understand the need of battery thermal management closely related with it. So this is how a lithium-ion battery would be typically looking like. So we need to thank Alexander Volta for this greater invention, which has been very much useful for this particular transition of electrical era. So he just initially tried the same battery working because of by means of zinc and silver, and it typically works on the principle of electrochemical potential. So if an atom has a tendency to lose an electron, or it is unstable by itself, if you provide a particular pathway for this particular electron and this particular ion, the flow of electron would gain electricity. So this is what is the basic idea of any battery. And among the electrochemical series present, lithium is having the higher tendency to lose an electron. So that is the reason why all the electric vehicle manufacturers are much more focusing on lithium ion battery in this current scenario. So lithium ion atom will have three electrons on its outermost orbit, among which one electron have the higher tendency to lose its tendency to a greater level. So lithium is highly reactive. You just try to place it in air or water, it would start to react at a very faster rate. It means it has the tendency to lose one particular electron immediately. So that is the reason why always lithium would be tried to clubbed with any metal oxide to make it a stable atom. So in most often cases, it would be clubbed with a cobalt oxide or any other metal oxide in this current scenario. And the price rise of lithium-ion battery is not only because of the lithium demand, and also a minimal amount of price is contributed for the presence of the cobalt oxide and the other metal oxide also in this particular cell. And what we have to do is we need to provide such a pathway. If you're able to separate the lithium atom from this particular combination. So as I said earlier, lithium is highly reactive. So what you are supposed to hold it with an aid of a metal oxide. So here it is allowed to be an cobalt oxide. So if you are able to place it in between the cobalt oxide and if you're giving certain amount of energy to detach this lithium atom from this cobalt oxide, what actually happens is the lithium atom would start to get react, and it would be get converted into a lithium ion and an electron. And if you're able to provide two different pathways for the same, so you need to provide a pathway for this lithium ion and you need to provide a separate pathway for this lithium electron. So if you're providing a pathway for this lithium electron, this flow of electron will give you electricity. So this is the basic working of any particular battery, where you need to detach an electron from an atom and you need to provide a pathway for that electron. So this flow of electron will gain you electricity. So the base material would get varied, and among the electrochemical series, lithium is highly preferred because it is having a higher tendency to lose the electron. So to make it much more understandable, I will just present it in a different perspective in this particular slide. So assume lithium is a highly mischievous student and it is allowed to get clubbed with a cobalt oxide who is a staff. So they are just moving for a camp or any summer camp. So where you are having a dormitory over here. So as the day is set, what actually happens is the cobalt is chaff and the lithium is the mischievous student. So the lithium is allowed to get settled down in the dormitory and the cobalt is moving away from it for staying in their own hostel. So what actually happens is when the lithium is moved to this dormitory, as it is mischievous, it would get separated as lithium ion and an electron. So lithium ion and an electron. So closer to this geometry, what they have present is they have present a very big barrier like this, which is having a minimal gap in between this. So assume lithium is very thin. So lithium would travel in the horizontal direction, and in the opposite side, you are having a huge a garden or a swimming pool. So what these student is allowed trying to do is, once the day is set, when the faculty is moved away, so they are trying to jump over this barrier and come and play over here and get back to the original portion once the sun is rises. So in this particular case, what actually happens is once the cobalt is detached from it, the lithium would get detached from it and it would be converted into lithium ion and electron. And as the lithium is very lean, it would travel in the horizontal direction and electron would travel the outermost pathway to reach over here. And this playground, whatever I have mentioned over here, is nothing but the graphite, so which won't take part in this particular reaction. So it is just being a storage place to hold the lithium and ion and the electron. So the electron would travel the longest path and it will reach over here. So where the electron and the lithium would come and settle down over here. So once the sun is rises, what actually happens is they will once again get back to their original portion and get converted into lithium cobalt combination. So this is how a basic lithium ion battery explanation can be given in a simplest way. So here you can just see the combination of lithium with cobalt oxide. And here you can just see, as I mentioned, it can be either swimming pool or whatever the easiest explanation that you can have. And the blue color is nothing but the electron, and the green color is nothing but the lithium ion. So once you are connecting a battery to it, it will get a positive charge, and thereby the electrons would get attracted over here, and the lithium would travel in the horizontal direction, piercing the electrolyte. So the barrier is nothing but the electrolyte. So this lithium ion would pierce the electrolyte and come and settle down over here in the graphite. So once you are just making an opposite charge or connecting a load to it, the reverse would happen. So thereby all these would get back to their original state. So this is how the charging and discharging of the lithium ion battery actually happens. And the greatest invention at this particular point of time is a passivation layer of solid electrolyte interface is formed on the electrode surface from the decomposition of electrolyte. So once the first time when lithium is allowed to travel in the horizontal direction, that is piercing through the electrolyte, what actually happens is this lithium reacts with this electrolyte and form a solid layer on the outer side of the electrolyte. So that is what is known as the solid electrolyte layer. So that is once the first time when lithium travels in the horizontal direction interacting with the electrolyte, it forms a barrier or an additional cover on the outer side of the electrolyte, so which would act as a barrier for the movement of electron in the horizontal direction. So if the electron is allowed to move in the horizontal direction, it leads to short circuiting. So our only aim is you need to provide a pathway, a separate pathway for the electron, and you should not allow the electron to move at any point of time in the horizontal direction. So this solid electrolyte layer would be additionally acting as a barrier to restrict the movement of electron in the horizontal direction. And related to the battery issues, the rechargeable lithium-ion batteries are regarded as most suitable energy storage device because of its higher tendency to lose electron. It's highly preferable in this current batteries. Performance is closely related to temperature. So for a better example, you can just consider your mobile phone. Most often cases, all the mobile phones make use of lithium-ion batteries in this current scenario. So you can just sense the temperature rise when charging your battery and discharging your battery. If you just touch the outer panel cover, you can just see there is a temperature range rise. And when you're just playing any game or working on any YouTube videos or some other stuff by making use of mobile phone, you can just sense a very high temperature rise on the outer case or outer side of your battery. So it means that the performance of the battery is highly related with temperature, and the charge and discharge capability of the battery would typically affect the performance of your battery. And next is the thermal runaway, is the phenomena that leads to destructive consequences such as rapid temperature rise, gas generation, and even battery explosion. So this thermal runaway is one of the reasons why the above accidents has been occurred. To reduce potential risk of thermal runaway, a variety of safety mechanism has been incorporated in this lithium battery, especially safety vents are incorporated, thermal fuses, automatic reset device, shutdown separator, chemical shutters, coatings, and heat retardant electrodes and electrolytes. So the need of safety vent is because of this electrochemical reaction, especially if you're just focusing on lead acid battery, there is a possibility forming of hydrogen gas because of the electrochemical reaction present inside. So there would be a vent on the head of the battery to release these particular gas. So this safety vent is used to release the gas that actually produced because of the electrochemical reaction. And thermal fuses, automatic reset device, and coating or heat retardant electrolytes. So because of this high temperature issue, the electrolyte or the separator would be coated by any heat retardant material to thermal runaway process. And you can just see the formation of the solid electrolyte layer on the outer side of the electrolyte. So this solid electrolyte layer would restrict the movement of the electron in the horizontal direction. And I hope you are very much aware that they would always ask us to charge your battery of mobile phone or laptop to 100% initially before using it for the first time. It means that they are asking all the lithium ion to travel on the horizontal direction and allow it to get react to the electrolyte and form a solid electrolyte layer on the outer side. So if you just try to charge it for the 50% and allow it to start to form a cyclic process, then the solid electrolyte percentage occurrence on the outer side of the electrolyte would be very minimal. So that is one of the main reasons why they are suggesting to charge your battery 100% before making use of the first usage. So that means you are trying to push all the lithium ion on the horizontal direction and allowing it to get react with the electrolyte and form a strong solid electrolyte layer on the outer side of the electrolyte. So in the thermal runaway process, the heat releasing reaction will let the battery temperature increase, and gas accumulation in the battery will cause the internal pressure to increase. So these are the major battery issues that actually happens when dealing with the lithium-ion batteries. And what is the role of battery thermal management system in this particular case? So the battery is the key operating tool to drive EV. The performance of EV actually depends upon the performance of the battery. So by means of the capacity of the battery, the operating period, the discharge rate, the power density. So all these four contribute to a maximum level on the performance of the battery. And one of the biggest issue with the battery is that it generates heat during charge and discharge period. So that we might have even faced on your day-to-day life itself. Try to charge your mobile phone for a time scale. If you just try to touch the outer case of your mobile phone close to the battery, you can just sense an high temperature occurrence. And similarly, think about downloading an high-end or high-end game or high graphics game in your mobile phone and try to play it for a short duration of time. If you just try to play it for a short duration of time, it would drastically discharge a huge amount of power. At that meantime, you just try to touch the outer case of your mobile phone, you can just sense a very high temperature. It means that the lithium-ion battery, not only lithium-ion battery, so the battery in general would generate heat during charge and the discharge period. So this charge and discharge period should be monitored very keenly to maintain or to monitor the performance of the battery. So the operating temperature of an EV varies between the temperature range scale of -40 degrees Celsius to 60 degrees Celsius. But the desired operating temperature range of an EV is around 15 to 35 degrees Celsius. Your battery, lithium-ion battery, would operate at a temperature range of -40 to 60, but the highly desirable condition to get an optimal output lies between the temperature range of 15 to 35 in order to get the optimal temperature output. So that is the reason why even the Apple manufacturers are suggesting to remove the panel cover and asking you to charge your battery. So when you try to put a panel cover and charge your battery, what actually happens is, because of the charging cycle, it would generate heat, and the main impact of having a battery cover is it would be acting as an insulator. So it will try to trap the heat inside your battery, and it will increase the overall temperature of the system. So that is the reason why you have been asked to remove the panel cover and charge your battery in all part of time. So if the temperature goes beyond 35 degrees Celsius or below 15 degrees Celsius, then the battery need to be thermally managed. So we are very much clear about the desired operating temperature range of the lithium-ion battery that is used in EV. So that lies between 15 to 35 degrees Celsius. So you need to incorporate a system to this battery, so that should maintain the temperature between this particular range. So if it exceeds 35, then what you have to do is you have to introduce a cooling system. When it falls below 15 degrees Celsius, then you have to introduce a heating system. So the alternate cooling and heating system that is incorporated in the battery to maintain its temperature level is what the role of battery thermal management system. So the battery need to be thermally managed to maintain the temperature within the operating range, but also keep the temperature below the safety limit of lithium-ion battery cell, that is 60 degrees. So it should never exceed the 60 degrees. So once it exceeds the 60 degree, then the alarming of battery degradation would start to a greater level. So we'll be much more focusing on lithium-ion batteries alone. Apart from that, nickel cadmium, nickel metal hydride, lead acid are also used in this particular scenario, but our target will be focusing much more on lithium ion battery in this particular range. And I hope now you are having the clear idea about what is the role of battery thermal management system and what is the need for thermally managing the battery. And we will try to understand what is the impact when it falls below 15 or move above 35 degree in the real-time case. So let us assume this is a pictorial representation of the series hybrid drivetrain, where you are having an internal combustion engine. From there, by means of the power electronics, the electrical energy is given to the motor, and thereby the rotational energy is given to the transmission system, and it is stored in case of a battery pack. And assume you are in an European condition where the temperature falls below -5 degrees Celsius. So we are very much aware that the battery would get an optimal operating range between 15 to 35 degrees Celsius. So once the temperature falls below -5 degrees Celsius, what you have to do is you need to incorporate a heating system to it to raise the temperature from -5 to 15 degrees Celsius. If you just see this pictorial image very clearly, you can just see there is an air blower present into it. So by means of a heater, heat the air and try to enhance the outer case of the battery pack to achieve this particular temperature range. So this is what actually occur in case of a cold climatic condition. And what about the impact of high temperature condition? So we are very much aware about that. Once the battery exceed 60 degrees Celsius, then the impact of the battery degradation would allow to get started. So at 85 to 120 degrees Celsius, the solid electrolyte layer would start to get decomposition. So at 120 degrees Celsius, the graphite anode will start to get react with the electrolyte. So till 120 degrees Celsius, the graphite won't take part in the reaction. So both lithium and electron will come over here and will stay there for a time, and after that they will get back to their initial portion. But once it exceeds 120 degrees Celsius, the graphite would start to get react with the electrolyte. So there would be an minimal percentage of graphite, the barrier, that is the electrolyte, would start to degrade. So there would be an option for the electron to either pick an horizontal direction or an outermost direction. So you're giving an electron a choice whether you need to travel in horizontal direction or in the outermost path. So accordingly, there is a huge possibility for the formation of short circuiting. And 130-degree, the separator would allow to start get melted. So in between the electrolyte, you will have a separator which would act as an additional barrier for the movement of electron in the horizontal direction. And after that, at 140 degrees Celsius, the electrolyte volatilization would happen. And at the time at 150 degrees Celsius, the cathode decomposition would happen. So the lithium carbon cobalt oxide would decompose at 150 degrees Celsius. That means the cobalt oxide would not able to hold the lithium along with. So lithium would allow to start to get react. So that would also affect the battery performance. At 200 degrees Celsius above, the electrolyte decomposition would happen. So because of this issue, whatever the battery fire issue that I have addressed in the earlier case might have happened. So that is the reason why they have called upon all their vehicles, and they have on this particular issue on trying to optimize it and trying to safeguard the battery and the market to a greater extent. But in real time case, the differential temperature should occur. So beside either it can be low or high temperature performance, a uniform temperature distribution is another key to ensure battery life. So good temperature uniform MITI should be maintained for the cell module and the pack level. So here you can just see the accident occurrence because of this high temperature issue. It is seen that one particular battery has been bursted, and that has typically affected the most of the batteries, and a complete battery fire issue has been occurred in this particular vehicle. So the battery temperature should be monitored, and it should stay well below this particular range, and it should never exceed the safety limit of 60 degrees Celsius. And once it started to exceed 60 degrees Celsius, there is a huge possibility for thermal runaway. So this is the reason why the battery thermal management is a key part that to be addressed when discussing about the electric vehicle in an elaborative way. And as we are in an high temperature region, so we will be focusing much more on the cooling system in an elaborative way. Sorry for it. So the cooling system is achieved either by means of liquid cooling, air cooling, or by means of solid as the phase change material based cooling. So it can be direct, indirect, air by means of natural convection, or by forced convection. And in case of PCM, it can be either based on the transition phase or the material composition. So these are the reason technologies based on cooling system that has been incorporated in the electric vehicle for the battery thermal management system. And I'll be focusing in an elaborative way based on the use of phase change material in the battery thermal management system. So the material with significantly large value of phase change enthalpy, especially the latent heat of fusion for melting and solidification, has the capability to store a large amount of thermal energy in small form factor. So if you just see this particular image, let us assume the water is at 0 degrees Celsius, and once it achieve 100 degrees Celsius, it won't be completely allowed to get vapor. So you need to maintain at this particular temperature range for a constant time period. So thereby your water will be converted from 100 degrees Celsius of liquid phase to vapor phase. So this particular constant temperature zone is what effectively utilized for the battery thermal management system of the EV. So how much amount of heat is required for this phase change material? We will try to understand this initially and try to quantify it in terms of number and have an interesting idea about it. So the state of matter is lies between liquid, water, and vapor. So if you are adding energy to this ice, you can just convert it into water, and if you add additional amount of energy to it, you can just try to convert it into vapor. And the reverse is also possible in this particular scenario. But in this transition period, you need to provide a constant temperature addition to change this phase from a solid to liquid or liquid to gas or back gas to liquid. And this all falls under the endothermic and the exothermic process. And we will in general coin this as melting, vaporization, and in inverse we will just coin this as condensation and freezing. So how much amount is required for this phase change? So here I have just come up with the energy versus temperature plot for the water. So the formula for calculating the specific heat capacity is QMC P del T, and the formula for calculating the heat required for the phase change is Q is equal to ml. So the water is initially at 0 degrees Celsius of liquid, and this is at 100 degrees Celsius of liquid. And after that, you have a temperature addition, and after that, it would be get converted into vapor. So this constant temperature addition requires a huge amount of energy as of compared with raising the water from the temperature of 0 degrees Celsius to 100 degrees Celsius. So in this particular case, there won't be no temperature change, and the heat addition would be handled by means of a potential energy. So let me just try to deal it with numbers. So determine the amount of heat absorbed by 1 kg of water to change the phase of from liquid to vapor. So your water is at 100 degrees Celsius of liquid, and your aim is to convert this 100 degrees Celsius of liquid to 100 degrees Celsius of vapor. If that is the case, the mass is 1 kg. The latent heat of vaporization is 2256 into 10 power 3 joule per kg. And the formula for calculating the heat is Q is equal to mLV. So because as the temperature is not varied, so the temperature is not be taken into account for this particular formula. If that is the case, the heat required is Q is equal to 2256 into 10 power 3 joule. And in the vice versa case, how much amount of heat is needed to raise the temperature of 1 kg of water from 0 degrees Celsius to 100 degrees Celsius. In the previous case, we have been trying to convert the water at 100 degrees Celsius of liquid to 100 degrees Celsius of vapor. So where you might have talked about the X values varies from 0 to 1 in your steam table plot. And that is what is the phase transmission from liquid to vapor. And talking about raising the temperature of a water from 0 degrees Celsius to 100 degrees Celsius, the mass is 1 kg, Cp is 4186 joule per kg degree Celsius, and the temperature rises from 0 degrees Celsius to 100 degrees Celsius. So the formula for determining it is Q is equal to mCp del T, where mass is 1 kg, Cp is 4186, and the temperature is 0 to 100, so T is 100. So in this particular case, whatever the energy that is required to heat the water from 0 to 100 degrees Celsius is only 108.6 into 10 power 3 joules. But whatever the energy that is required to convert the water from 100 degree of liquid to 100 degree of vapor is merely 4 times higher than whatever occurs over here. So this is what is the importance of phase change material. So this phase change transition requires an enormous amount of heat to get converted from one phase to other phase. So at this time scale, a huge amount of heat can be trapped from the system to acquire this particular process. So that is the reason why the phase change material is having an important role in the battery thermal management system. So one among such phase change material is the organic PCM. So the organic PCM can be paraffin and non-paraffin. The former involves a fatty acid, alcohol, ester, and the glycol. So in most often cases, think about the candle in your home. So if there is a power cut, if you are having a candle, that candle would light for the whole day, whole night itself. So assume you're lighting the candle at night 10 o'clock, and it will be even igniting till 3 to 4 o'clock in the morning. So it means that the conversion of your solid PCM to liquid, especially candle, takes enormous amount of time. So it means that you can trap more amount of heat to convert from one particular phase to other particular phase, and it is having a lower thermal conductivity. You can even hold the candle closer to your the flame in the hand. So it means that the thermal conductivity is also very minimal, and this phase transition occurs at a very huge time scale. So that is the reason why the organic PCM, particularly paraffins, are highly preferred in the battery thermal management system. So rather stable, safe, and have high latent heat of fusion, and also they are available in large temperature range, which makes them compatible with most construction material. And here I have listed out certain materials, especially paraffin. So one interesting disadvantage is, as it is paraffin and fatty acid content, it has an higher possibility to form a flammable part. And as I described earlier, it is having a very low thermal conductivity. It won't conduct the heat, but it will trap the heat itself and try to convert from one particular phase to other particular phase. So here I have just listed out the time conversion required for converting the liquid paraffin at T is equal to 0 and try to convert it into a completely solid phase. It requires maximum of 90 minutes. So this much amount of constant temperature addition, heat removal must be given to the system to convert your liquid into solid phase. And in the inverse case, it took nearly 40 minutes to convert your solid PCM into liquid form. So this particular time limit is what we are interested, and at this time limit, it would uh, trap a constant amount of heat to convert it one phase to the another phase. And here I have listed out one particular research article that is very closely related with whatever I have listed earlier. So the thermal management of a lithium ion battery using carbon fiber PCM composite. So the maximum allowable for lithium ion battery to be less than 60 degrees Celsius. So the primary objective of the study is to synthesize a PCM with proper melting point range and high latent heat to effectively observe the heat generator within the battery. So the paraffin wax exhibit sufficient thermal energy storage density and suffer from low thermal conductivity. So what in this particular study they have conducted is they have taken a paraffin wax along with that carbon fiber, and they have tried to melt it and add few percentage of carbon fiber along with it. And the study they have tried to do is they have considered a small chamber, and in between that they have poured the paraffin wax and they have placed the battery inside, and along with that they have connected the charging and discharge unit and try to charge and discharge it at a different rate. And because of charging and discharging, the battery would be allowed to get heated, and they have placed thermocouples closer to battery and the phase change material and try to monitor the temperature impact with respect to the charging and discharging cycle. So this is one simple study they have carried out. And if you just see it, they have placed the temperature at three different ranges. One is at a radius of 7 mm, and another one is radius of 9 mm, and another one is radius of 11 mm. So considering this as the chamber and the battery in the center, so they have placed the battery at three different radius inside the chamber. So one over here, one particular circle, and one this in particular circle. So in all the cases, they have introduced a thermocouple and they have made charging and discharging rate and try to observe the temperature rise. And what is the impact of the phase change material with respect to the charging and discharge cycle has been noted out. So as expected, the rate of temperature growth in the simulator surface is higher at the beginning and gradually diminished as the time elapsed, because the conversion of solid to liquid occurs in the similar fashion when you are introducing a phase change material closer to the battery. But the changes would be much more evident only when the temperature reaches the melting point of the paraffin. So the melting point of the paraffin would be around close to 40 to 45 degrees Celsius. So till 45 degrees Celsius, you won't face any drastic temperature profile. But once you achieve the temperature range of 45 degrees Celsius, you can just sense there is a formation of straight line. It means that a more amount of heat is trapped in this particular zone. So overall temperature of the system would get reduced because of this particular incorporation of phase change material closer to the battery. And they have once again to vary the fiber mass ratio and try to conduct the same study, and they have tried to vary the fiber length and allow to conduct the same study. So with respect to this, they have of the battery thermal management system of the battery. So here I have given you the real-time image of it. Here you can just see they have taken a chamber and placed the lithium ion battery inside it, and they have melted and poured the paraffin wax into it, and they have tried to incorporate the thermocouple and the charging and discharge unit closer to it. So because of charging and discharging, various charge and discharge, there would be an high temperature rise, and they have studied what is the impact of temperature on the cell and the PCM with related to it, and whether it can withstand this particular temperature limit is what they have monitored. And this is what talks about the organic PCMs. In the previous case, what they have tried to do is they have just tried to deal it with the pure phase change material alone. And there is also inorganic PCM, where inorganic PCM are named composed of inorganic molecules, and the typical examples of making use of hydrated salts and metallic PCMs. So you can just deal it with either hydrated salts or having a metallic mesh like this that is dipped inside the paraffin bags. So one of the key disadvantages of these inorganic PCMs are inorganic materials have attractive characteristics, and not only the purpose of a wide melting temperature range, and also they are thermally safe as of compared to the phase change material. And it is having high heat rate, and the disadvantage is the stability of the material would start to get degrade based on the thermal cycling. So you'll be adding heat and removing it. So because of this particular, the material properties would get varied. So now we'll try to understand this with one interesting particular study. So study of high power lithium ion battery using porous metal foam saturated with phase change material. So what they have tried to do is they have considered a phase change material. Along with that, they have tried to incorporate a porous metal foam, and here you are having the battery module. So in between the batteries, initially they have tried to pour only the paraffin wax. So that is the candle wax. They have melted it and poured that in between the cells. And in the second case, they have placed a mechanical mesh in between this. So where the mechanical mesh is initially dipped in a melted paraffin chamber. So they have melted the paraffin and they have dipped this mechanical mesh and they have placed in between the cells. So they have conducted the study only for cell number 5 and cell number 9. So they have placed a thermocouple close to cell number 5 and cell number 9, and they have conducting a sale. So initially cooling has occurred by means of a natural convection. So that is, they have wouldn't use any PCM or PCM with metallic foam. So here the battery are placed in a minimal distance between each cells, and the air is acting as the medium for cooling. If that is the case, they have tried to charge the battery for initial 100 minutes and allowed to cool for next 100 minutes. So as I described earlier, at the time of charging, you will have a drastic temperature rise, and after that, at the time of cooling that is kept idle condition, there would be a drop in temperature. And after that, they have tried to discharge the battery in next 50 minutes itself. So they have tried to discharge the battery in next 50 minutes. That is 100% state of charge, state of health to a 20% or 10% of state of health. So what they are trying to do is they have completely drained your battery percentage from 100 to either 20% in next 5 minutes. So if you are trying to discharge the battery at a very faster rate, what actually happens is there is a huge temperature range. Here you can just see they have the temperature for cell number 5 and cell number 9 especially. So for these two cells they have kept and thermocouple, and they have connected it to a system where the temperature is monitored for every minute. So this has been plotted with respect to the time scale. So at the time of charging there is a temperature range, and the charging temperature is not enormously higher, because we are very much aware that the operating temperature limit for your lithium ion battery is 15 to 35 degrees Celsius. But at the time of charging, it exceeds to a minimal level. But at the time of discharge, it exceeds to a greater extent. And the safety limit, whatever I has mentioned over, is 65 degrees Celsius. So the lithium ion battery safety limit varies from 60 to 65 degrees Celsius. At this particular case, the cell number 5, sorry, cell number 5 exceeds the safety limit of the lithium ion battery when you are just dealing with the natural convection. And this is for one particular study. If you are just able to vary the discharge rate at a different proportion, you will have a different plot with respect to this. And for all these cases, you need to estimate what is the temperature rise in the system. And after that, you have to incorporate a proper cooling system. Here we are just making use of and passive cooling system. I can just deal with active cooling system also. So here PCM is actually a passive cooling system where they have tried to incorporate the passive cooling system and try to trap that heat from the system. So this dramatic temperature rise is due to the low convective heat transfer coefficient of the air, because the air is having a very low thermal conductivity, and the suppression of the air motion is such and integrated in the battery module. So as the air is allowed to get heated up, it would not get a sufficient turbulent motion to get interact with all the parts of the cell, and thereby there won't be efficient cooling in this particular module. So this is what is the initial case study they have considered, or initial research issue they have identified. For this, what they have tried to do is they have introduced the pure PCM alone in this particular setup. So they have conducted once again the same charging, cooling, and discharge cooling cycle. In that particular case, for cell number 9, you can just see there is a drop in temperature. So it means that both for the air and the PCM material, the temperature rise would be similar till the 45 degrees Celsius, because the melting point of paraffin is 42 degrees Celsius. So till 42 degrees Celsius, you won't face a very big temperature variation between natural convection and the PCM based study. But after it exceeds 42 degrees Celsius, for converting from solid to liquid phase, you need to give an additional excess amount of temperature. So or that you need to give a constant temperature heat addition to the system. So for that, most amount of heat would be trapped by the PCM and it won't be liberated to the system. So that is the reason why there is a drop in temperature occurrence as of compared to the previous case. Here you can just see the temperature has fallen below 55 degrees Celsius as of compared to the previous case of 65 degrees Celsius. So in the previous case, the temperature rise was above 65 degrees Celsius. But when you are trying to incorporate a PCM to the system, the most amount of heat is required for the conversion of liquid to vapor phase. So during the discharge, especially for the time of 175 minutes to 230 minutes, when the temperature first increased from the ambient of 25 to the melting point of 42 degrees Celsius, the temperature increase rate declined because the solid paraffin wax began to melt, and the heat stored as the latent heat of the PCM is effectively used for the conversion of solid to liquid interface. And next, by making use of a copper metal foam. So in the previous case, the temperature, the maximum temperature rise of 52 degrees Celsius. So here they have just only plotted the discharge plot, because they have neglected the charging, cooling, and the discharge cooling cycle. The most of the concentration has been placed closely in the discharge. So if you just see it very clearly, from the atmospheric 25 degrees Celsius to 42 degrees Celsius, the temperature pattern of either natural convection, the black one is the natural convection, and the red one is the pure PCM, and the violet color is the incorporation of metallic foam to it. So in all the cases, this follow a similar pattern, but once it exceeds the 42 degrees Celsius, you can just see there is a drop in temperature for the PCM and PCM based metallic foam as of compared to the natural convection. So this is what is the role of phase change material in the battery cooling system. And further, the study has been focused on for a different discharge rate. So till 25 to 42 degrees Celsius for all three, either it can be natural convection or making use of a pure PCM or dealing with a metallic foam, they follow a similar trend. And after that, it would be allowed to started to get melted. So at this melting range only, you can just sense there is a drastic change in the temperature profile as of compared to the previous two cases. And after that, it would follow a similar trend where it would be get converted into liquid. And because of this particular case, you can just get rid away from the safety limit of the lithium-ion battery operating temperature zone. And herewith, I have presented you the initial natural convection study for cell number 5, the temperature exceeds the safety limit of the lithium battery operating temperature range. So that is, it is around closely to 70 degrees Celsius. But if you just try to incorporate the PCM to it, the temperature has fallen to 52 degrees Celsius for the same operating condition. And when you just try to incorporate metallic foam with PCM, the temperature has further reduced to 43 degrees Celsius. Oh, sorry, 48 degrees Celsius. So here you can just see the temperature transition from 70 degrees Celsius to 42 degrees Celsius, because without making use of any external source of energy to thermally control your battery temperature limit. But we have not till achieved the optimal temperature range of 15 to 35. But just introducing PCM along with metal foam, we are able to achieve this particular point of. But whatever the cell I have presented over here is allowed to be in rectangle type of block. And the current research progress that is allowed to be happening is they are trying to incorporate along with the phase change material and an aluminum enclosure. So you'll have an aluminum enclosure and close to it a PCM module, and inside it you will have a battery cell. So this would be able to thermally manage your cell when it is in cylindrical format. And they are also recent research progress is also working toward incorporation of a nanoparticle or having fins closer to the battery or the metallic foam like this. So this is what we have discussed in the previous case. You will have a metallical foam like this that is dipped inside the PCM. So these are the recent research progress that is actually happening in the current scenario. And this fins can be either an L type or V type or Y type or X type. So a number of patterns of fins are also allowed to be studied for understanding the heat transfer rate based on the different discharge rate of the battery. So with this, I'll just try to conclude my presentation on the research progress on the battery thermal management system using phase change material in EV. And in most often cases, I have referred this particular textbook. And for making the presentation, I have crossed over these reference book and the research article. And if you have any further queries related to this topic, you can just ask us of now. And if you need to know further, you can just try to ping me through this mobile number and email ID.
Okay.
And I would like to open the session to the audience as of now.
Okay, thank you, Dr. Dinesh. It was a wonderful lecture. We have a couple of questions in chat box. There is a question from Suraj. During battery use, let's say PCM's phase is changed from solid to liquid. Then when PCM get back to its original phase, that is solid?
Yeah, it is really an interesting question. So that is one of the major issue when you are just trying to deal with the PCM. So that is the reason why they will have a closed module present next to the PCM. So it won't allow to cool further, and it won't allow to get melted. So now people are working on hybrid cooling. So you will have a PCM, and next to that you will have a liquid coolant. So once you sense that your PCM is allowed to get converted into pure liquid phase, it will just change its shape. So that way all the PCM would get melted down and settle down. So if that is the case, they will get switch on to their liquid cooling, and this liquid cooling will be passing on an alternate side to get back to its solid phase. So of the issue related when you're just dealing with the phase change material. So for this particular case, they are just moving to hybrid cooling. So you will have phase change material, and in the opposite side, you will have a liquid cooling. So this liquid cooling would be switched on only when you sense that your phase change material is completely get melted down and changing its original shape. So once it changes its original shape, it will settle down, and there won't be an even interaction with the battery throughout its profile. I hope I have answered for Suraj. Sir?
Yeah. So the next question is, will thermal be the reason for failure of one of the cell in a stack or any other reason?
Thermal would be one of the reason. We can't just address that it is one of the reason alone for having the thermal management issue. And even Tesla is making use of merely AAA battery size cells as jack below the footers of the drivers and the co-passengers. So the reason why they have convert all their cells into merely AA or AAA battery size is because to thermally manage it. So as you are making the surface area allowed to get enhanced, so you would have a better cooling as of compared to having an rectangular block based cells. So that is the reason why they have moved over it, and they are making use of liquid cooling with and curved copper plate touching in most of the surface area of each and every cells. So it cannot be addressed only because of this particular thermal runaway issue. It can be any issue, but in most often cases, it is because of the thermal runaway issue. And each and every cell differs based on the manufacturing and the discharge rate. So it might one particular cell might get discharge to a great level, or one particular cell might get charged to an over level, but they will anyone have an battery BMS system to maintain all these processes. But even at one particular case, if there is any issue with related to one particular cell, it would typically get to thermal runaway, and it would have an impact on the nearby cells.
Okay.
I hope I have answered for Krishna, sir.
Yes. So the next question is whether fast charging will damage the battery. What will future update for fast charging for vehicle?
No, fast charging won't typically affect the battery at a greater rate. I believe Apple has moved. Apple mobile phones have moved to fast charging, and they are not even providing chargers in this particular scenario. And if they are providing it, they are just providing only 5-watt chargers, and they are also having 10-watt and higher watt chargers. And you might have seen numerous ads that you can charge your mobile phone in half an hour and 1 hour. So based on if you just recharge your battery completely to 0 to 80% at a very faster rate, and after that the charging would be at a very minimal point. So this fast charging will help to increase the charging rate till 80%, and after that, based upon the cell, it would typically get varied.
So there is one request from Suraj. Can speaker spend minutes or so again on discussing how heat is liberated during charging and discharging?
So because of the movement of electron in the outermost orbital path and lithium movement on the horizontal direction, the flow of electron would typically liberate heat. So if you just you can just sense it with any copper coil in your household application itself. So when there is a flow of electron occur in a copper coil, then there would be a liberation of heat that is very much aware about it. And what actually happens in the discharge rate is the flow of electron would be at a very faster rate when you are just discharging it. So that is what is 1C, 0.5C, 2C, 3C. So I have not get further into it. So the discharge rate, once you vary the discharge rate, that is you are just draining the charge from 100% to 0% in 1 hour, in half an hour, in 10 minutes, in 15 minutes. If you do these particular process, the flow of electrons from one particular direction into other direction would be at a very faster rate to handle that particular load. So at that point of time, especially at the time of discharge, the heat liberation would be enormously high. And when you are just trying to charge your battery, you will try to collect the power from your and make use of your power adapter. You will just ask the electrons to move at a steady rate. And when you're just dealing with the fast charging, the flow of electron rates would be somewhat varied. But for a normal charger, you will be asking your battery to flow your electrons at a constant rate. So that is the reason why when you're just dealing with the charging, the temperature is somewhat minimal as of compared to the varied discharge rate. I hope I have answered for that particular question.
Yeah, if you have any other follow-up questions, you can unmute and ask.
Can I come in? I am Palani Balaya here.
Yes, of course, sir.
I can elaborate a bit more along with Dr. Balasubramanian about the heat generation in the cell. In fact, this is one of our extensive research area as well. Is that okay, Dr. Balasubramanian?
Yes, sir. I'm really happy to.
Yeah. So the total heat Q is actually made of reversible heat and irreversible heat. Reversible heat is basically because of the entropy changes in the electrode material. If you have lithium cobalt oxide, when you are removing lithium, the remaining cobalt oxide undergoes certain entropy change. So that is actually reversible. So when you remove the lithium, it has some change, heat generation. When you put back the lithium, it reverses. Whatever the amount of heat that is generated, it comes back. So it's a reversible heat generation. The irreversible heat generation is because of the polarization processes, whatever I discussed in my talk. That is actually proportional to I square R. R is the internal resistance of the battery, the cell. So I square, it goes as a square. The higher the current you pass, I square R will be larger. So you have to see what is the cause for the internal resistance. There are many causes for the internal resistance. One is the solid electrolyte interface formed on the anode. Second is the charge transfer from the electrolyte to the anode, as well as lithium ion from the electrolyte to the anode, and the electron from the copper current collector to the anode. So these are the two things that are being transferred to the anode. So you have lithium ion movement, or rather transfer, and then you have electron transfer. So put together, you have so-called charge transfer resistance. So this is the second one. First one is the solid electrolyte resistance, because solid electrolyte resistance is resistive to electron. It is ionically conducting, but resistive to the electron. Second one is the charge transfer resistance. The third one is the lithium ion as well as the electron movement within the particle. It's called diffusion, chemical diffusion of the lithium. Lithium comprised of lithium ion and the electron. So chemical diffusion of all these three put together will give you what is called internal resistance. So that is our internal resistance. If the internal resistance is high, then I square R, which is the irreversible heat loss, is also high. So you can't charge at a high rate, you can't discharge at a high rate. That's why we have to always keep the internal resistance of the cell as low as possible. So that is I square R, which is the irreversible heat loss. Then there is so-called reversible heat loss because of the entropy changes. These two put together give rise to so-called heat generation during the charging and discharging.
Okay. Yeah, okay. I think you have answered his query, sir.
So I believe that is the reason why we have moved into high voltage system rather dealing with high current system for the overall EV operation.
Yeah. That is a very good point. So people don't want to use high current, rather they are going for high voltage. They minimize the current operation, the current that is passing through the circuit.
So the resistance would liberate enormous amount of heat. So that is the reason why they have switched over to high voltage for the overall operation of your EV, for even powering your accessories also. So that is the reason why the overall battery model is known as high voltage system.
So this is a very important talk actually. When you want to do so-called thermal management system, there are two ways to minimize. One is like what Dr. Balasubramanian talked. It is the external thermal control. External thermal control. It could be PCM. It could be porous material. It could be water cooling, air cooling. Everything is external to the cell. The second one is internal control of the heat generation. That is what ATAL. So there is I square R plus entropy changes put together gives you total Q dot. Total Q dot is the heat generation. So internally, one can control also by increasing carbon content, by providing proper connective path for the electron movement, and then lithium transfer, electron transfer, and then minimizing the CI. One can also control internally within the cell. And when you are looking at advanced research, you have to control these two. Can I reduce the heat generation within the cell, that is internally, but there is a limit. After that, you cannot minimize it at all. Then we have to rely upon external heat control, thermal control, like what Dr. Balasubramanian talked. Yeah, thank you. Thank you for allowing me to give explanation.
Oh. Thank you, Balaya, sir.
Thank you very much, sir.
Any other questions? If you have any other questions, you can unmute and ask, or you can type in the chat box. Okay, I think there are no more questions. I thank Dr. Dinesh Balasubramanian for your wonderful talk. We will have one more talk. We are going to have one more talk from Dr. Dinesh tomorrow. That will be the third session in the afternoon. So thank you, sir. Thank you, Dinesh. for
Okay, so I would like to express the heartfelt thanks to the management, principal, and the organizer for giving me such an opportunity. And I believe I didn't bore you for past 1 hour and above
no,
by
of
having
course
this
not.
lecture.
Of course not. It was delight to listen to you.
Okay, sir. Thank you very
Okay,
much. And
okay.
I hope we'll just see back on for the tomorrow's day's session also. Thank you very much.
Yeah. Thank you. So for this announcement is for the participants that today's third session is being handled by trainers from Isha Foundation. They are offering one of their corporate event, corporate offering. So it will be a very nice session. So please do join at 1:30. Thank you. I'll end this meeting here. Thank you, Dr. Dinesh. Thank you,
Thank you very
Dr.
much.
Balaya, sir, for attending.
You are welcome.
Sir, same session only, sir.
Yes, yes.
Same link only, sir.
Yeah. Same link for all the sessions. The link will be same for all the sessions. Okay.
Okay, sir. Okay.
Thank you.
Thank you, sir.